Hello dear students. So yesterday we had done division algorithm, and we have seen how given any two integers a and b, where b is non-zero, there exist unique integers. Okay, the symbol represents unique q and r inside z such that a is equal to b q plus r. Okay, where r lies between 0 and modulus of b. Okay, so that was basically the division algorithm. So say if I take r equal to 2, then given any integer a, okay, given any integer a, I can say there exists unique integer q such that a is equal to b into 2. I take q equal to 2. Sorry for that. B equal to 2 means I am taking 2 as the divisor. Okay, so given b equal to 2, and so for all integer a there exist q and r such that a is equal to 2 into q plus r, where r lies between 0 and 1. Okay, that is r is equal to 0, 1. Okay, so only two options are there if we take b equal to 2. So considering divisibility by 3, we have the values of r will lie between 0, 1 and 2. Okay, like that. So if we consider divisibility by a number n, the value of r lies between 0, 1, 2 up to n minus 1. Okay, these are the only possible remainders. So from here you see any integer a can be written as twice q plus 0, or a can be written as twice q plus 1. Okay, these are the only two options, right? So this integer is even integer, and this integer is odd integer. Okay, similarly any integer, if we consider divisibility by 3, any integer can be written as 3q plus 0, or 3q plus 1, or 3q plus 2. Okay, these are the only three ways we can write any integer. Okay, similarly any integer can be written as 4q plus 0, or 4q plus 1, okay, or 4q plus 2, or 4q plus 3. Okay, when you go to 4q plus 4, this is actually equivalent to the form 4q plus 0. Okay, because 4q plus 4, it can be written as 4 into q plus 1. Okay, so our quotient is changing, plus 0, right? So that is the meaning. So if we consider divisibility by 5, then we can write any integer in 5 different forms. Okay, these are the only possibilities. So this concept will be used to solve certain problems. Okay, say for example this, show that the square of any integer is of the form 4k or 4k plus 1. Okay, square of any given integer is of the form 4k or 4k plus 1. Okay, so we will use division algorithm to justify this. Okay, so that means square numbers or perfect squares cannot be of the form 4k plus 2. Okay, they cannot be of the form 4k plus 3. Okay, these two are not allowed. Okay, so how to solve it? You see, any integer a is of the form so let us use that 2q or 2q plus 1. Okay, so any integer is either even or odd. Okay, so we are considering divisibility by 2 here. So any integer a is of the form 2q or 2q plus 1. So if a is equal to 2q, then what about a square? A square, so I have to show the square of any integer is of the form 4 into something. Okay, so a square is equal to 2q whole square, right? So and this can be written as 4 into q square. Okay, so 4 into q square means q square is an integer, so it's of the form, which is of the form 4k, which is of the form 4 into some integer. Okay, so here let me write 4k or 4k plus 1, where k is a integer. K is actually a natural number. Okay, k belongs to natural numbers union 0, say, but k is greater than or equal to 0, right? Square cannot be negative, so of course it can be 0, so k can be 0, right? So which is of the form 4k, 4 into some integer k. And if a is of the form 2q plus 1, in that case, then your a square is like 2q plus 1 whole square. Okay, so it's 4q square plus 4q plus 1. Okay, so if we take 4 common, it is like 4 into q square plus q plus 1. Okay, so comma, which is of the form, so just replace q square plus q by k. Okay, means it's some integer which is of the form 4k plus 1. Okay, right, so this is, we are done. Any integer, square of any integer is of the form 4k or 4k plus 1. Okay, similar to that, let us try another one. Show that the square of any integer is of the form 4k or 8k plus 1. Okay, so of course this k, everything, they are integers, right? So this is also similar, very similar. I'll tell you. So any integer a is of the form a equal to of the form twice q or twice q plus 1, right? So if a is equal to twice q, then a square is equal to 4q square, we have already seen, which is of the form 4k. Okay, so first part is done. And if a is equal to twice q plus 1, then your a square is equal to 4q square plus 4q plus 1. So we will just modify this. We can take 4q common, so q into q plus 1 will remain. Okay, now you see I have to show that it is of the form 8k plus 1, so that means I need another factor of 2 from here. So if q has got two options. Q is either even or odd. If q is even, then from here I can take 1 2, right? If q is even, q will be of the type 2 into something. Okay, and if q is odd, then q plus 1 will be even. Okay, so in any case, q into q plus 1 is always even. Okay, so let us write that part. If q is even, then q into q plus 1 is even. Okay, is even. And if q is odd, okay, then odd number plus 1, that is an even number. Okay, then q plus 1 is even, and so q into q plus 1, that is also even. Okay, is even. That means in either case q into q plus 1 is even. Okay, so let q into q plus 1 equal to 2 into some, say, n. Okay, 2 into n for some n belongs to integers. So therefore a square is equal to 4 into q plus 1 plus 1, right? So this can be written as 4 into twice n, or I could have written k itself directly. So let k in q into q plus 1 be written as 2 into k for some k integers. So this a square can be written as, right, this one, k plus 1. So I can write this as 8k plus 1. Okay, so which is of the form, so it's required, which is of the form 8k plus 1. So a square of any integer is either of the form 4k or 8k plus 1. Okay, now see some application of this. So note that perfect square, so from the above result we get that perfect square is of the form 4k or 4k plus 1. Okay, these are the only two possible ways of writing a perfect square. Okay, so hence from here I can conclude the contrapositive statement. Okay, perfect square implies it is of the form 4k or 4k plus 1. Okay, the contrapositive of this statement is if the integer is not of this form, then it cannot be a perfect square. Okay, because if it is a perfect square, it has to be in this form, right? So hence a number of the form 4k plus 2 or 4k plus 3, okay, cannot be a perfect square. Cannot be a perfect square. Right. So say something like 1, 3, 7, 8, 9, and I write something like okay, 34. Okay, something like this. 1, 3, 7, 8, 9, 3, 4. Is it a perfect square? Is this a perfect square? So you see, I can write this one as 1, 3, 7, 8, 9, 3, 4. This can be written as 1, 3, 7, 8, 9, 0, 0 plus 34. Okay. So this part is divisible by 4. Why? Because the last two digits are 0, right? So this part can be written as 4 into some number q, okay, plus, because this part is 1, 3, 7, 8, 9 into 100. So 100 can be written as 4 into 25. Okay, so this part is divisible by 4. So 4 into q plus 34. Instead of 34, I can write 4 into 8 plus 2. Okay, so it is like 4 into q plus 8 plus 2. So it is of the form 4k plus 2. Okay, so it cannot be a perfect square, not a perfect square, because if it is a perfect square, it has to be of the form 4k or 4k plus 1. Okay, so a number of the form 4k plus 2 cannot be a perfect square. Okay, right. So this is one possible application of this. So another problem that we can do is say cube of any integer. Okay, square of any integer. We have, yeah. So let us try with squared again, or I'll give you this to try at home. Show that square of any integer is of the form of an integer is of the form 3k or 3k plus 1. Okay. And then let us try this. Show that cube of an integer is of the form 9k. Cube of any integer is of the form 9k or 9k plus 1 or 9k plus 8. Okay, so if you divide the cube of an integer by, or say if you divide a perfect cube by the number 9, then the only possible remainders are 0, 1 and 8. Okay, actually if you divide a number by 9, the possible remainders are 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, but if it is a perfect cube, it will have only this 3 remainders. Okay, so we can show it using our division algorithm. So after making cube, I need something like 9k. Okay, so I can start with divisibility by 3. Once I make cube, I'll get something like 27k cube. Okay, so I don't have to start with 9k divisibility by 9. Okay, if you start with divisibility 9 by 9 also, you will get the similar type of result, but you have to check 9 different forms. Okay, so a smarter way is to start with divisibility by 3. So any integer a is of the form 3k or say 3q or 3q plus 1 or 3q plus 2. Okay, so now we will test one by one. If a is equal to 3q, then what happens to a cube? A cube becomes 27q cube. Okay, so I can write this one as 9 into 3q cube. So this 3q cube I can replace by k, okay, which is of the form 9k. Okay, so or alternatively you can write it this way: 9 into 3q cube. So in the next step you can write which is equal to 9k, where k equal to 3q cube. Okay, so you can write it this way also, or you can write which is of the form 9k. It's all the same, right? And then the next one is if a is equal to 3q plus 1. Okay, then what happens to q cube? A cube. So a cube is 3q plus 1 whole cube. So it's 27q cube plus so a cube plus 3 is squared b. So 3 into 3q squared into 1 plus 3ab squared. So 3 into 3q into 1 squared plus 1. So it's 27q cube plus 27q squared plus 9q plus 1. Okay, so I can take 9 common. So 9 into, it's 3q cube plus 3q squared plus only q plus 1. Okay, so it is of the form 9k plus 1, where k is equal to 3q cube plus 3q square plus q. Okay, so for a equal to 3q plus 1, we have got that the cube is of the form 9k plus 1. Okay, and if a is of the form 3q plus 2, in that case a cube is equal to, so you break it similarly, 3q plus 2 whole cube. So it's 3q whole cube plus 3 into 3q square into 2 plus 3 into 3q into 2 square plus 2 cube. Okay, so this can be written as 27 into q cube plus 27 into 2q square plus 9 into 4q plus 8. Okay, I don't need the products, so I have not multiplied. So it's 9 into 3q cube plus 6q square plus 4q, right? So please correct me if I am wrong. I'm just writing it down. You please do it yourself. Plus 8. Okay. So I can write it in the form 9k plus 8. Okay. Where what is this k? K is equal to 3q cube plus 6q square plus 4q. Please check the calculations. Okay. The system is this. So we have shown that every cube of any integer is of the form 9k or 9k plus 1 or 9k plus 8. Okay. So similarly you can try this also. Show that the fourth power of an integer is of the form 5k or 5k plus 1. Okay. Fourth power of an integer is of the form 5k or 5k plus 1. So I'll give you this as a home task. You try to do it. So you start with divisibility by 5. So any integer is of the form 5q or 5q plus 1 or 5q plus 2 or 5q plus 3 or 5q plus 4. So you have to test all these 5 possibilities. Okay. So first you test it for square. You find out what are the possible forms of square. So if it is of the type 5q, then it is of the type 5. Say instead of using k, you use k in the final form. So instead of using k here, you use something else. Say 5p. If a is of the form 5q, then a square is of the form 5p. And if in this case it is of the form 5p plus 1. And here 5q plus 2, when it is 5q plus 2, I think most probably you will have a 4 here in the last, right? So it is of the form 5p plus 2. And when you have 3 here, it will be 3 square in the last term. So 3 square is 6. So that 6 can be written as 5 plus 1. Okay. So I can combine that 5 with the earlier terms. So it is of the form 5p plus 1 only. Okay. And when you have 4 here, 4 4s are 16. So 16 can be written as 15 plus 1. So 15 can be combined with the earlier term by taking 5 common. So it is ultimately of the form 5p plus 1. Okay. So square of any integer is of the form 5p plus 1 or 5p plus 2. So your possibilities are reduced. Next you test it for a to the power 4. A to the power 4, you square it, it is of the form 5k. If you square it, this will be of the form 5k plus 1. And this one 5p plus 2, if you square it, it will be of the form sorry, I wrote it in a wrong way. This square of 5q plus 2, it will be of the form 5p plus 4. Okay. So so if you square this now it will be of the form 5q plus 1. Okay, 5k plus 1. So please do it that way. Okay, it's quite simple. Okay, right. So let us try another problem, something like this. Show that 3a square minus 1 is never a perfect square. Is never a perfect square. Perfect square. Okay, any number of the form 3a square minus 1 cannot be a perfect square, right? Okay, so how to solve it? So we have already seen square of any integer is of the form 3k or 3k plus 1. Okay, we know square of any integer is of the form of the form 3k or 3k plus 1. Okay. So if a square is of the form 3k, then what about 3a square minus 1? 3a square minus 1 will be like 3 into 3k minus 1. So which is like 3 into 3k. Can I write it in a different way? I can write it as minus 3 plus 2. Okay. So I can take 3 common. So it's of the type 3 into 3k minus 1 plus 2. Okay. So which is of the form? Which is of the form, say 3q plus 2. Okay. And so a number of the form 3q plus 2 cannot be a perfect square, because perfect square has to be of the form 3q or 3q plus 1 only. Okay. And so it is not a perfect square. Not a perfect square. Okay. So similarly, the other part I can do it here itself. If a square is of the type 3k plus 1, okay, then 3a square minus 1 will be like 3 into 3k plus 1 minus 1. So it's 3 into 3k plus 3 minus 1. So it's 3 into 3k plus 2. Okay, so again the same conclusion you can write, which is of the form 3q plus 2, and so it is not a perfect square. So any number of the form 3a square minus 1 is never a perfect square. Right, so these are a few applications of division algorithm. Right, so let us try some more. Show that any prime, show that a prime greater than or equal to 5 is of the form 6k plus 1 or 6k minus 1. It is of the form 6k plus 1 or 6k minus 1. Okay, if you have a prime number, right? So here you see we consider divisibility by 6. So any integer is of the form is of one of the, so instead of writing 5 odds, let us write it this way, is of one of the following forms, is of one of the following forms. Okay. What are the forms? It is 6k, or say let us write it with q, 6k, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, or 6q plus 5. Okay, so any integer, say a. So if a equal to 6q, then a is not prime. Why it is not prime? Because it's divisible by 6. A is equal to 6 into some quantity, so it's divisible by 6. A prime number cannot be divisible by any other number except itself and 1. Okay, so 6 is not a prime number, so 6 is already divisible by 2. Okay, so you already have some idea about prime numbers from your school days. Okay, so of course we'll do it in more detail here. So using that idea, 6 is not a prime number. Okay. So if you get a number which is divisible by 6, it cannot be a prime number. Okay. So n is not prime as 6 divides a. 6 divides a. Right. If a equal to 6q plus 2, so let us just single out the cases where it is not possible. Okay. If a is of the form 6q plus 2, okay, then it cannot be a prime. We are already given that the number is greater than or equal to 5. Okay. If a equal to 6q plus 2, then 2 divides a. Okay, but So 2 divides A, but I cannot conclude from here itself that A is not prime, because 2 itself is prime. Okay. So here, what do I need? I will need to use this. But A is given to be greater than or equal to 5. Yeah? So A cannot be prime. Okay, A cannot be prime. Right. If A equal to 6q plus 3, okay, then this will be like 3 into 2q plus 1. Okay, so which is divisible by 3. Then A is not prime. A divides, then 3 divides A, and A is greater than or equal to 5. Okay, so A cannot be prime. A is not prime. Okay. So see, prime greater than or equal to 5 can be written in this form. Okay, 2 cannot be written in this form. 2, if I write 2 as 6k plus 1, then it will not make any sense. 6k will be equal to 1, so k is 1 by 6, but k is an integer, it cannot be 1 by 6. Okay, so except 2 and 3, the other integers, other primes can be written in this form, 6k plus 1 or 6k minus 1. Okay, so if A equal to 6q plus 4, okay, then so this is equal to what? This can be written as 2 into 3q plus 2. Okay, so A 2 divides A, 2 divides A, and A is greater than or equal to 5, so A cannot be prime. Okay, A cannot be prime. Okay, so the only other possibilities, thus if A is prime, then it can be of the form 6. What are the remaining ones? 6q plus 1 or 6q plus 5. So here I cannot take anything common. Okay, so 6q plus 1 or 6q plus 5. Okay, but 6q plus 5 we can write it in a different way. This can be written as 6q plus 6 minus 1. Okay, so I can write it as 6 into q plus 1 minus 1. Okay, so it is of the form 6k minus 1. Okay. So equal to say 6k minus 1. Therefore, any prime greater than or equal to 5 is of the form 6k plus 1 or 6k minus 1. Okay, right. So don't get confused that whenever a number is of the form 6k plus 1, it will be a prime. Okay, that is not correct. If it is prime, then it will be of the form 6k plus 1 or 6k plus minus 1. The other way it is not true. If a number is of the form 6k plus minus 1, it may not be a prime. Okay, say for example something like say 6 into 3 or 6 into 4, yeah, 6 into 4 plus 1. Okay, what is that? 24 plus 1, 25. 25 is not a prime number, okay, but it is of the form 6k plus 1. Okay, so it's just a one-way implication. If a number is prime, then it will be of the form 6k plus 1 or 6k minus 1. So we can the contrapositive is true. If a number is not of the form 6k plus 1 or 6k minus 1, then it cannot be a prime number. Okay? If a number greater than or equal to 5 is not of this form 6k plus 1 or 6k minus 1, okay, so it cannot be a prime number. Say something like 38, it is of the form 6 into 6 plus 2, so it is not a prime number. Okay, because if it is a prime number, it has to be of the form 6k plus 1 or 6k minus 1, but 38 is of the form 6k plus 2, so it cannot be a prime number. Okay, right. So this also we have done. Another one, let us try. This also you can try at home. Show that the cube of an integer, integer is of the form 7k or 7k plus minus 1. Okay, so here you are left with no other options, but you have to check all these possibilities: 7q plus 1, 7q plus 2, up to 7q plus 6. All these 7 possibilities you have to check. Okay, so please do it. It's not that difficult. So let us try this. Prove that no integer in this sequence is a perfect square. No integer in the following sequence is a perfect square. Okay, what is that? 11 11 1 1 1 1 1 1. Okay, 1 1 1 1 1. 5 4 ones, then 5 ones, like that. Okay, number of ones is increasing, so no integer here is a perfect square. Okay, so how will you do it? Say something like 11. So we will use that concept. Any perfect square is of the form 4k or 4k plus 1. So 11 can be written as what? 4 into 2 plus 3. So it is of the form, which is of the form 4k plus 3. So it's not a perfect square. So it is not perfect square. Okay, so before starting you can write it something like that. We know any integer or any perfect square. Okay, any perfect square is of the form 4k plus. Please write it. Okay, I'm not writing. Any perfect square is of the form 4k or 4k plus 1. Okay, so here 11 is 4k plus 3, so it cannot be a perfect square. Similarly 1 1 1, this is equal to what? 4 into 100, 4 into 25 plus the reason I am writing it this way is this. Okay, let us separate it this way. 4 into 111 can be written as 100 plus 11. So this is 4 into 25 plus this is 4 into 2 plus 3. Okay, so it's something like 4 into 27 plus 3. So this is also of the form 4k plus 3. Okay, so it's not a perfect square of the form 4k plus 3. So therefore 111 is not a perfect square. Not a perfect square. Okay, so in general, let us take one. So what is the trick? You see, you just separate the last 2 digits. Okay, so in general, say 1 1 1 1 1. I do not know how many ones are there. Say n ones. Okay, n ones. This can be written as what? 1 1 dot 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 1 and then 0. So how many ones I have taken? N minus 2 ones. Okay, plus 11. Okay, so this is obviously 1 1 1 1 1 this into 100, right? So here I have n minus 2 ones plus 11. Okay, so this is 1 1 1 into 4 into 25. Okay, plus this is 4 into 2 plus 3. Okay, so I can take 4 common, so it is of the form 4k plus 3. So it is not a perfect square. So 1 1 1 up to n0 n ones is not a perfect square. So we have shown the general case. Okay, we have taken a general term of this sequence which contains n ones, and we have shown that it is not a perfect square. Okay, right? So we have done almost all the exercises which are given in this book. Yeah. Okay, so I'll give you 2 more problems. You can try doing it. For n greater than or equal to 1, establish that n into 7n square plus 5 is of the form 6k. Okay. Another one, if n is odd show that n to the power 4 plus 4n square plus 11 is of the form 16k. Okay. Or this could be given in some other form. Show that this is divisible by 16. Okay. Or show that this is divisible by 6. Okay. So please try it. N into n into 7n square plus 5, it is of the form 6k always. Okay, so maybe you can try with odd and even. If you take even number here, so it's of the form 2q, and this will be of the form 28q square plus 5. Okay, so can we take 3 common from here? Right, so yeah, see if this can be done without, of course it can be done by taking all possible forms of this divisibility by 6q plus 1, 6q plus 2. You can test all the 6 and then establish. Okay, just see if we can do it in an easier way. And this one, it is already given that n is odd, so you just substitute. I think it will work, because here it will be 2q plus 1 whole to the power 4. So from here the constant term is 1. Here the constant term will come out as 4. So 4 plus 1 is 5. 5 plus 11 is 16. So you will get 16 common here. Okay. So please try these problems.